This chopper is appropriately named because everything about it is way over the top. With its ridiculously wide 15-inch rear tire and the ultra-long 5-foot forks. What else could it be called other than overkill? Does a chopper really need a dragster tire on its rear end or such a high frame? Not really, but does a roadster really need a Hemi? You know where I'm going with this. Go big or go home. Sometime back in 1990, I sat around a campfire with my sketch pad and pen, going over designs for the ultimate bicycle chopper. I eventually came up with Blade Runner, a chop with knife blades for spokes, a circular saw blade for a chain ring, and multiple sharp objects all over the frame. Cool, yes, but too expensive to build. Eventually, I came up with OverKill, a chopper that took everything about choppers and pushed it to the outer edge of extreme. I build my bikes using mostly recycled junk, and there were many fat car wheels in the scrapyard, but nothing that jumped right out. The problem was going to be adding the bike hub to the car rim without making some big ugly disc plate to hold it all together. Spokes would, of course, be the best solution, but would this even be possible with a car wheel? When I arrived home from camp that weekend, lo and behold, some dude had left me a humongous old car wheel in the trash bin out in the laneway behind my garage. Yes, it was badly rusted and the tire was weather worn, but I knew it would fit the build perfectly since it was so over the top. It looked as though the entire center of the rim was made of aluminum or some alloy, and the outer ring of the rim was solid steel. Now, this opened up a new can of ideas for using bicycle spokes in the rim. As shown here, I pounded out the rim center with my favorite adjusting tool, and it came apart like an over-baked cookie, sending fragments of what looked to be aluminum all over the garage. Considering how easy it was to break the rim, it amazes me to think that it could hold a 3,000-pound car up around a high-speed corner. So far, my evil plan was coming together nicely. After a few minutes of fun hammer bashing, the center was removed, and what remained was the basic steel outer rim and tire. Not only was the rim in great shape, minus the rust, but there were no holes or welds on the inside where the aluminum insert was removed. Because of this simple design, I would be able to drill holes and add spokes to the inside of the rim, then paint it if necessary. If you look at most basic steel car rims, the insert is welded along the inside edge of the rim, so to use that type, you will have to grind away the 4 or 5 welds and then fill and grind the area. This is how I made the other car wheel choppers shown on the chopzone.com plans page. With this huge rear wheel as the base for this chopper, I could build the rest of the design around it. After all, it was going to be a bit of work to make a frame to hold such a monster-sized wheel, and to solve the chain line problems soon to come. Since building to me is part art and part science, I decided to forge ahead on the frame rather than overthink the little details. As you can see in here, I bent up 4 90-degree elbows using my shoe bender and some inexpensive 1-inch thin-walled electrical conduit from the hardware store. This conduit, called EMT, is great stuff for general bicycle frame building. The EMT bender I am using costs about $20 at the hardware store. After bending the conduit, I had 4 identical 90-degree elbows. The only requirement of the parts is that when they are welded to the main tube, there is ample clearance around whatever size rear wheel you plan to use. The actual measurements don't really matter because the goal is to build your chopper frame around the rear wheel you have. So make your best guess and cut all tubing a bit longer than needed. Here are the 2 elbows, and a length of 1.5-inch EMT will form the main tube of the frame. This is the backbone of the chopper and will determine how tall and how long the bike will be. Again, there is no magic number for the length of this tube. I just found a piece that I knew was much longer than it needed to be so that I could cut it down to size later. Choose a main tube that is longer than you can reach with your hands, assuming you were sitting directly at one end of it. Place the two elbows near the end of the main tube so that the distance between them is at least 4 inches wider than the widest part of the tire. This will allow 2 inches of clearance per side of the tire for things like the chain and any cables to be run. Once the two elbows had adequate clearance for my rear tire, I ground out the ends slightly with my angle grinder so that the joint between the larger tube and the ends of the conduit would have no gaps. The 3 tubes were laid on a flat piece of plywood for welding. Notice the use of welding rods as guides to place the elbows at the proper height. The elbows are 1 inch in diameter, and the main tube is 1.5 inches. Tack welds were made to the elbows at first, taking a measurement from the center of the main tube to each end of the elbows to ensure parallel alignment. With only a single tack weld holding the elbows to the main tube, it is easy to bend them into place. Also, remember that electrical conduit has a thin galvanized coating, so all welding should be done outdoors or in a well-ventilated area. I visually inspected the parallel alignment of the two elbows and the clearance for the rear wheel. Visual inspection is a necessary skill, and you can't always trust the measuring tape, especially if a part is warped on only one side. You can read a number incorrectly, but you can never fool the trained eye. Once you are satisfied with your work, the final welding can be done. Take your time to avoid heat distortion, checking your work often along the way. As shown here, the finished and ground the welds on the elbows and main tube. Normally, I save all welding cleanup and grinding until the end, but since this part of the frame is easily accessible at this stage, it was easy to do. When cleaning and grinding welds, be careful not to take too much metal off because you can easily weaken the weld if you grind to a level lower than the original metal. Ugly and chunky welds can still be strong. Since I was working from a crude sketch with no real plan, I mocked up different parts of the work during the build to make sure I was on track. During these mock-ups, I sometimes make radical changes to the plan as new ideas formed. This image shows the first half of the rear triangle and the main tube propped up by a piece of scrap tubing. By doing this mock-up, I was able to figure out what length to cut the main tube, and also the overall height of the frame by sitting on the rear tire and reaching ahead as if there are a set of handlebars on the bike. When I found a main tube length that I thought was good, I cut it and then measured the total height from the floor. This is what I based the rest of the build upon. The bottom half of the frame, let's call it the boom tube, is constructed almost exactly the same way as the main tube, except that the two elbows are on a slight upwards angle in order to form the rear triangle. Again, no high-tech methods were used to determine the length of the boom tube at this time. I just made sure there was more than enough length there to cover my leg length, also known as inseam. Inseam, in the most basic term, is the distance from where you sit to the farthest point you expect to reach when pedaling. If you make this too long, you will have a hard time reaching the pedals. A simple way to figure out your inseam for this project is to sit on the edge of a chair, reach out with one foot as though you are pedaling, and have someone draw a tape measure from the center of your seat to the underside of your foot. Cut the boom about 12 inches longer than you need. The clearance between the boom tube and the ground was about 3 inches. The boom tube and its elbows were welded, ground, and tack welded to the ends of the main tube and its mating elbows. Although the design is totally up to you, I wanted my boom tube to be parallel with the ground. This means that the bottom bracket will end up higher than the boom tube, as you will see later on. The two sets of elbows that make up the rear triangle were tack welded solidly in place, but not yet fully welded. Flexing or redoing a tack welded joint is much easier than cutting a fully welded joint. And since I was working without a final plan, I thought this would be the safest method in case I had to break the welds and adjust tubing. At this stage, there has to be a connection between the boom tube and main tube to complete the frame. This will be called the down tube. The three tubes, main tube, boom tube, and down tube, will form a basic triangle, giving great strength and rigidity to the main frame. For a little style, I decided that a slight bend at the intersection of boom and down tube would be nice, but how could I to bend this 1.5-inch tubing? The simple answer was, I couldn't. 1.5-inch thin-walled conduit is extremely strong tubing that can't be bent without a large hydraulic bender, so I decided to use a pre-bent elbow from the hardware store. With the factory bent elbow welded in place, I joined the down tube to the boom tube as shown here, and the basic frame was now complete. The rest of the design would simply involve filling in the blanks and connecting the dots. The next step involved figuring out how long and at what angle the front forks needed to be so that I could weld in the head tube. Check out the crazy rise on that chopper frame. To get the head tube at the correct angle, I needed to know the desired length of the front forks, the height of the bike, and the size of the front wheel, all of which I knew at this point. Since I knew that my front wheel would be 26 inches in diameter and the front forks were to be 5 feet long, I only needed the exact height of the frame, and this was easy to get by mocking the frame back up again, so the boom tube was parallel to the ground at a height of 3 inches. As shown here, I simply propped the frame up to the correct height using whatever was lying around the workshop. I also placed the rear wheel in the frame to make sure I was on the right track. Remember, the junction of the rear triangle should be near the center of the rear wheel, as this is where the dropouts will connect to the wheel axle. To connect the forks to the frame, you will need a head tube, which can be salvaged from any old bike frame. I chose a fairly long head tube from an old mountain bike frame that was used on another project, but just about any head tube will do the trick. If you are new to bike part salvaging, there is a full tutorial called frame chopping on the chopzone.com forum. Once your head tube is cut from the frame and ground clean as shown here, put it away for later. You do not want to weld this to your frame yet, since without the front forks and wheel installed, you will have no idea what angle to attach it at. Let's get those front forks built now. The first step in creating the front forks is to find an actual set of bicycle forks that fit correctly into the head tube that you cut up previously. If you have the forks that came from the bike used, then great. If not, just make sure the threads are long enough to allow the proper hardware to be mounted correctly. I did not have the matching front forks, but did find a set that would fit just fine. Once you find the correct size for the head tube, hack the legs off as shown here. You only need the fork stem, so cut the legs, and grind the crown area clean. There are also many tutorials on the chopzone.com forum showing how head tubes and many other bicycle components work in case you are new to this. OverKill uses a traditional triple tree fork where the base of the fork stem is affixed directly to the fork legs. This is similar to the way a standard bicycle fork is made, except that there will be a top support as well for strength. The fork legs will be joined to the base of the fork stem using some leftover flat bar I found in my scrap pile. The flat bar that I used is 1.5 inches wide and 1/4 inch thick, but something slightly lighter would have also worked just fine. You can use just about whatever you want for this part, even tubing if you like. The flat bar is cut into two 1.5 inch square pieces and then joined to the base of the fork stem on a slight angle, as shown here. The angle is not critical, just choose something that allows the fork legs to be positioned about 1.5 inches or so in front of the fork stem. The final distance between the ends of the two pieces of flat bar should also be about 5.5 inches, about the same width as the front wheel hub. The two fork legs will now be welded to the fork stem by means of the two pieces of flat bar you just worked on. My fork legs are made from two 5-foot long lengths of 1.25 inch electrical conduit. There are two things we need to make sure of here. First, the distance between the centers of the fork legs should be about the same distance as standard front dropouts, about 5.5 inches. And second, both fork legs need to be as parallel to each other as possible. To keep the fork legs parallel, I first laid them on a flat surface and then welded a bit of square tubing at each end as shown here. The centers of the fork legs are exactly 5.5 inches apart, and both fork legs are perfectly parallel to each other. With the two fork legs held together by the square tubing, I welded the fork stem in place while still on the flat surface. You will notice the top of the fork legs are farther up than the top of the fork stem. This is because my plan was to have the handlebars become part of the fork legs. This will become clear later on in the building process. In a typical triple tree setup, the top of the fork legs would be slightly lower than the top of the fork stem, so a plate could fit around the fork stem, then bolt to the top of the fork tubes. When welding the fork legs to the stem, make sure that the stem is parallel to the fork legs. Look at it from the side and then lengthwise to ensure this. When you are sure of alignment, weld it in place. Practically any salvaged dropouts can be used to attach the front wheel to the fork legs, as long as they allow adequate clearance between the hub and the fork leg. I cut this set from the rear of an old kid's BMX bike frame. Make sure that both dropouts are of equal size as well. Grinding them together in a vise helps to ensure they are both the same. You could also make your own dropouts from some steel plate if you wanted something a little more fancy looking. Weld the dropouts to the front fork legs while they are bolted to a front wheel, as this makes alignment easy. Any front wheel that is straight will do the trick. Place the dropouts dead center on the fork legs and make sure the front wheel is parallel between the legs before you start welding. A tack weld on each side is usually enough to hold the wheel in place for visual inspection. The amount of fork that extends past the dropouts is up to you, but keep in mind that this affects frame height. Once the dropouts are firmly tack welded to the fork legs, it's a good idea to visually inspect everything for alignment before laying down the heavy bead. Hold the forks directly in front of you and look down the length to make sure the wheel looks parallel. If all looks good, weld the full length of each dropout, then remove the wheel and then weld the other sides. I like to weld a small tube about an inch above the front wheel, as shown here, as this helps reduce fork twist and allows for the mounting of a fender if needed. Because the front forks are so long, it may not be enough to just rely on the front wheel axle bolts to hold everything together. This little tube will add a great deal of rigidity to the forks. To complete the top of the triple tree, you will need to cut the end from a bicycle gooseneck. The gooseneck shown here is typical of many inexpensive mountain bikes and came with a slightly curved handlebar, which is perfect for this bike. Make sure the gooseneck is steel, not aluminum, as you will be welding it. Since I had the mountain bike handlebars handy, I decided to cut them in half for later use. I used a pipe cutter to cut each half away from the center area, so that later I could weld them directly to the tops of the fork legs. Another bit of scrap flat bar will be used to create the top support for the triple tree forks. This flat bar will not take the same forces as the lower support, therefore does not need to be as thick. I have chosen flat bar 1.5 inches wide and 1/16 of an inch thick. It is cut 5.5 inches long so that it rests against the center of the fork legs. Once the flat bar is cut and rounded off, it will be welded to the small section of tubing cut from the bottom of a steel gooseneck. As shown in here, this small section of the gooseneck needs only be long enough to fit into the fork stem an inch or so. To ensure alignment, the piece of flat bar and gooseneck stem are welded in place like this. The flat bar should fit snugly against the fork legs, yet not be so tight that it cannot be placed without great force. Notice how the ends of the flat bar do not protrude past the center of the fork legs. This way they will not be noticeable when the forks are viewed from the front. 2 holes are drilled into the flat bar and fork legs so that a pair of machine screws can hold the assembly in place. Since the force will tend to push the fork legs against the flat bar, only small machine or wood screws are needed, just to keep the unit from sliding out of the fork stem. The gooseneck bolt is actually not necessary, and is only held in place by some tape on the inside of the tube. It is basically acting as a plug for the top of the gooseneck stem. To create my trick handlebars, I cut the clamp heads from 2 old steel goosenecks, which will be welded to the fork leg tops, and each one will hold a handlebar half. I could have just welded the handlebar halves directly to the fork legs, but this would eliminate the ability to adjust or interchange the handlebars. Also, the tops of the fork legs would still need to be capped somehow. To ensure that both handlebar halves were aligned properly, I placed them in the clamps and then tack welded each clamp using a single weld. It was easy to bend the clamps slightly, correcting any misalignment before adding the final welds to the clamps. The clamps are placed on a slight inward angle to approximate the general feel of a relaxed set of cruiser handlebars. Once I was happy with both the positioning and alignment of the handlebars and clamps, the final welding was completed. This filled up the holes at the top of the fork legs, as well as adding some style to the design. With this system, practically any size or shape handlebar could be split in half and placed on the bike, opening great possibilities for later experimentation. This was a good time to finish and grind all the welds on the forks since they were already on the workbench. The dropouts, fender support, handlebar clamps, and triple tree members are all fully welded and cleaned up using a grinder flap disc. Remember to check your work for alignment as you weld, since the heat generated by the welding process can really distort things. The front fork dropout shifted slightly when the inside bead of weld was added, but this was still well within acceptable tolerance, since both of them moved an equal amount. Don't be afraid to cut a part off and re-weld it if it seems to be too far out. And often a few hits with a hammer will take care of the problem. Although it's an optional part, I decided to add a seat tube to my frame, which is the curved tube just ahead of where the rear wheel sits. On a full-size motorcycle, this tube adds strength to the frame and offers a place to add engine mounts. Here it was done just for looks. A bit of tubing with a 1-inch diameter was in my scrap bin. The curve matches the approximate diameter of the rear tire. Getting the proper angle for the head tube was easy at this point since the front forks were complete. The head tube, bearings, and hardware were placed onto the fork stem, and then the frame was again propped up to the correct height by stacking some scrap boards under the boom. With the front wheel installed and tire inflated, the forks are set into place, and then the head tube is tack welded to the frame. Before tack welding the head tube to the frame, the proper fish mouth is cut from the joint at the main tube and down tube so that welding can be done properly. Once you are satisfied with fork to frame alignment, final welding and grinding can be done as shown here. The small rod is being used as a gusset. It is a chunk cut from the top rail of an old shopping cart. A bolt or flat bar would also work. It was now time to concentrate on the rear wheel. This had to be done before the rear dropouts were installed in order to achieve the proper frame height. At this point, I thought I would be painting the inside of the rim due to the large amount of corrosion, so sanding was the first place to start. After sanding off the chunky rust with sandpaper, I realized that the rim was actually not that bad off. No deep pits or scratches, just surface rust. Surface rust can usually be removed by sanding with multiple grits of sandpaper, working your way down to 220 grit and then steel wool. After a few hours of heavy manual labor, the rim came back to life, and it was evident that painting would not be necessary. Sure, it's not a perfect showroom polish job, but it isn't bad either. Once the spokes were in place, the rim would look as though it was brand new. Speaking of spokes, you will notice that there are 28 holes drilled around both sides of the rim, just inside the lip, for a total of 56 spoke holes. To figure out where to drill the holes in the rim, I used another ultra low-tech method typical of my building style. I laid an old 28-hole kid's bike rim up against the edge of the car rim and drew a point by eye from the spoke hole in the bicycle rim to the top of the car rim. I then punched a mark on each dot and then drilled the hole. Just like that. Here's the hub that will be used to spoke the giant car wheel. Nothing more than a cheap steel rear hub removed from an old warped kid's bicycle wheel. With each hub half placed 15 inches apart, it is essentially going to be like two full bicycle wheels side by side. Because this hub had 14 holes per side, it would work out perfectly if I drilled in between each hole, creating a hub with 28 spokes per side, essentially 2 wheels worth of spokes. The hub was first separated by removing the tube that joins the two halves. This is easier to do than you would have thought. In fact, the first half came off just by twisting it by hand. Not much holding these hubs together except the tension of the spokes. The tube was pulled from the other half of the hub simply by twisting it out with vice grips. Now I am left with the two hub halves and the bearing parts. So how do you double the number of spoke holes in a hub? Well, you just take a sharp punch, estimate the position of the hole between two existing holes, then give it a whack with the hammer. Then take your drill and drill out the spoke holes on the punched marks. The hub shown on the left now has 28 holes. With both hub halves drilled to double the number of spokes, the next step was to create a hub wide enough for the 15-inch fat car wheel. A piece of 1-inch diameter tubing was cut to a length that would allow each hub half to clear the outside of the tire for chain clearance. This hub widening tube does not need to be extremely heavy, as the weight is carried only by the axle and spokes, but do make sure the axle will fit inside. The hub widening tube should be the same length as your rim is across the top. This places the hub flanges just outside the width of the rim. My rim was 15 inches wide across the top, so my hub widening tube is cut to 15 inches. Here it is, the world's widest bicycle hub at almost 18 inches wide. The center tube is simply welded to each hub, half making sure the two halves are as parallel to each other as possible. The hub was fully welded and ground clean at this point, since this was the last time I would be able to get at it. If you plan on painting the inside of the hub, then do it now. Where do you find a 2-foot long bicycle axle? Special order? Machined on a lathe for $200? No, you make it yourself using an old shopping cart rail and an old bicycle axle. Yes, that's the top railing from a shopping cart, cut to the correct length so that I can weld the two axle halves to each end, creating my own custom bicycle axle. Like I said in the introduction, I promised there would be no expensive or hard-to-find parts on this bike. Just junk. Any steel rod of 1/2-inch diameter or so will work. The key here is to get the axle stubs welded to the extension rod as straight as possible in order to make the wheel sit perfectly on the bike. This is not that hard to do. Just tack weld the axle stub to the rod, then roll it along your workbench, banging it totally straight with a rubber mallet or light hammer. Once straight, repeat the process again until fully welded. Here is the part that was actually a lot easier than I thought it would be. Wheel lacing. The fact is, this was my first attempt at custom bicycle spoking, and after talking to many professionals about what I was attempting to do and getting little more than a blank stare or laugh, I was wondering if it was at all possible. I knew that I would need 56 spokes. That part was easy. How long should they be? I found 2 old 20-inch kids' bike wheels and removed 56 spokes from them. They were a little rusty, so I took the steel wool and made them look brand new. I decided that the most logical thing to do would be to shove a spoke into every second hole and see what happened. Well, after no more than 10 minutes, the thing was looking like a bicycle wheel, as shown here. I just turned the spoke nuts 5 turns each, and then did the same thing on the other side. Even at this point, I could hold up the wheel, spin it in my hand, and it was almost 100% true. Notice how the spokes are all at the same angle. This is because the longer they are, the further the hub will turn to accommodate them. In fact, it's looking as though the spoke length does not even matter much here. Another 15 minutes and the wheel looked mostly completed. To finish the wheel, I only had to find a good distance for the next wave of spokes to cross, and then put them all in. Since the first set of spokes were placed in every second hole, I just did the same thing in the opposite direction, placing the first spoke in any hub hole, and finding a wheel hole that allowed it the same amount of angle, just in the opposite direction. Once the first wave of spokes is completed, every second hole spoked, then the others find their place. That's all there is to it. Next, I just kept turning each spoke nut 2 turns until every spoke was tight. The wheel was perfectly true after that. As long as all the spokes are tightened equally as you work around the rim, the wheel should end up nice and straight. Now that I had a rear wheel, it was time to get it connected to the frame. For this task, I would need to add a set of rear dropouts to the rear triangle of the frame. The easiest way to go was to salvage a pair from a scrap bicycle frame, something I had many of. I cut the dropouts from a bent-up road bike found in the scrap pile. Only the bare minimum was required from these dropouts, so I cut all the unnecessary metal away using a grinder cut-off wheel. To make sure both dropouts ended up exactly the same size, they were held together in a vise and ground flush at the same time. I bolted both dropouts to the wheel, held the wheel in place, then tack welded both dropouts to the frame. This method always ensures proper alignment and reduces distortion from welding. Once both outer sides of the dropouts are welded to the frame, the wheel is removed and the inner sides are welded on both sides of the joint. Although large enough for a small engine, OverKill will remain powered by pedals only. So a bottom bracket was in order. Here is a stumpy bottom bracket freshly hacked from some old mountain bike frame. It may seem like a lot of work to clean these things up, but in reality it takes only minutes with an angle grinder. Minutes later, the bottom bracket was clean and ready for installation. I started with a heavy grinder disc, taking away all but a sliver of the unwanted material. Then I switched to a sanding disc to clean up the excess tubing. The down tube was notched out about an inch in order to accommodate the bottom bracket. This allowed the bottom bracket to sit into the frame tube to a depth of about 1 inch. Plenty of weld area for strength. The straighter you make this cut, the easier it will be to get the bottom bracket installed properly. With the bottom bracket only tack welded in place at each end, alignment of the crank set is easy. I installed the bearings and crank arm, checking its alignment with the frame tubing. It should be parallel to the frame, or at least the same on both sides. Try to get the bottom bracket welded in place as straight as possible in order to reduce the possibility of a chain misalignment. Although bicycle chain is quite forgiving on slight misalignments, too much angle on the chain ring will cause nothing but frustration in the long run. At this point, it was easier to move the bike around if it was assembled as a rolling frame, so the front forks and wheel were installed. It felt good to see the basic chopper taking form. Motivation to work late nights on the chopper was high now. With the front forks and both wheels installed, this thing really started to look like a mean, lean, low beast of a chopper, and from this point on, the rest of the build will be easy. All I needed now was some type of transmission. It's hard to believe this is a bicycle. It looks like it could take a street bike engine. With most of the chopper completed, I could now start working on the transmission. On a normal bicycle, the chain runs from the front chain ring on the crank set directly to the chain ring on the rear wheel, but not on this beast. Because the rear tire was so wide, the chain would have to be offset a good 10 inches in order to get around the tire to the rear hub. An intermediate drive, also called a jack shaft, will be created that will take the chain coming from the crank sprocket and redirect it to the outside of the wheel via 2 sprockets joined by a shaft. Using the same method as used to make the ultra-wide rear wheel hub. I cut and rejoined the hub halves. Here you can see the 2 halves just before welding the bit of 1-inch tubing between them. Yes, this is the same part shown in the last photo. I just ground off the spoke flanges using an angle grinder. They would not be needed. Also, the black paint has all burnt off from the welding process, leaving the bare steel. With the axle widened and fully welded, 2 BMX free hubs are screwed into the hub as seen here. One of the free hubs is not only screwed to the hub, but it is welded as well. This is because it will end up on the wrong side, left side, and unscrew if it were not welded. The welded hub is not a free hub any longer, just a sprocket on a shaft. Again, the threaded axle must be extended to fit the new hub, so a bit of steel shopping cart rod is welded in between the 2 halves of axle. This is done in the same manner as before, making sure that everything is straight and true. Another set of salvaged frame dropouts are used to hold the jack shaft onto the frame. I chose rear dropouts because they allow for some horizontal alignment of the axle, and since 2 separate chains are used, I had to fiddle with both the alignment of the rear wheel and the jack shaft to ensure proper chain tension. The dropouts were welded to a bit of flat bar, then attached near the rear of the frame, as close to the wheel as possible in order to minimize their impact on the look of final design. Although this drive system is indeed cool, I did not want it standing out too much. By placing it near the back of the frame and painting it dark, it will be dwarfed by the huge black rear tire. The other dropout was attached to a small tube and welded to the elbow on the rear triangle. Once both dropouts were welded in place, I centered the jack shaft in the dropouts and cut chains for both sides. By cutting the chains to size while the jack shaft was centered, I would gain maximum adjustability both ways. In the end, the jack shaft ended up just about centered. All that was left at this point in the frame build was the small stuff: handlebars, seat, paint, and a bit of bling. Handlebar stubs were capped off at the ends using a few washers, then ground flush. I capped off the ends of all open tubing by either finding suitable plastic plugs or by welding something in the end. Here, a nice shiny pair of chrome lug nuts are used to cap of the rear frame triangle. The frame was first lightly sanded to cut into the thin galvanized coating of the conduit in order to ensure proper paint adherent, and then painted with gray metal primer. The gray primer was left to cure overnight, so it would be ready for paint the next day. Once the frame and all the little bits were dry, the bike was reassembled carefully and put in the corner of the garage to cure. Curing is a process that takes place after the paint first dries. I used high heat brake caliper paint because I liked the hot lime green. The paint was overkill, so it was a good fit. With the paint curing on the frame, now was a good time to cobble out a seat from some scrap plywood and foam. I could have plunked down a fat bicycle seat or banana seat, but after all of this hard work, OverKill deserved a special seat. Custom built to fit the bike. The seat base is a basic shape cut from a bit of paper and traced on both sides of some scrap plywood. The back of the seat was just a semicircle cut from the same plywood, then bolted to the base. Wood screws and glue hold the two pieces together. To stay with the theme of keeping all but the rear wheel as minimal as possible, a basic rat tail style fender was cut from a bit of 12-gauge scrap steel. The back of the seat was traced onto the steel, then an arc drawn along a line to form the shape which will be cut using a steel blade on a jigsaw. The fender was bent in an arc to follow the shape of the rear tire. This was done by placing the fender over the tire and pressing down on it until it is the correct shape. This steel is very easy to bend by hand, so getting the correct shape was a snap. The tip of the fender was also rounded out a bit to avoid a stabbing hazard. A bit of 1-inch foam was cut and glued to the plywood. Just about any old foam will work, but try to avoid that spongy light brown stuff. It's just too soft to be of any use. The edge of the foam is cut with a sharp razor knife, so it would be flush with the edge of the plywood. A square of vinyl large enough to wrap the top of the seat and a bit of the underside is cut and stapled to the nose of the plywood to start the upholstery process. The trick to a decent seat covering without sewing is to stretch the fabric as tight as you can around the foam while making sure to use plenty of staples. Folds and wrinkles around corners will disappear if the fabric is tight enough. You may have to pull up certain staples to pull the fabric even tighter as you work along the perimeter of the seat. The tighter the fabric is, the better the seat will look. Don't worry about the ugly underside full of staples. This will not be seen when the seat is on the frame. A few hundred staples later, and the seat is looking good. Because of all the stretching and stapling, almost all of the wrinkles are gone, and those that remain will be gone after a few rides. The bolt on the underside of the seat will hold the seat to the frame. This was installed before the foam. These cool gold thumbtacks can be found at any fabric or thrift store. The tacks give the seat a professional look, hiding the fact that I really know nothing at all about doing upholstery. The next step would become one of the hardest things I have ever done, putting a car tire on by hand. Yes, I know after I spoke the rim that a tire machine would not be able to install the tire, but I had no idea how much work getting this thing on would be. I'm not going to lie to you. It was a lot of work. The job started well as shown here. I just duct taped around the spoke nets to protect the inner tube. Yes, you need one of those. And slid the first half of the rim into the tire. What a breeze. The inner tube is needed due to the fact that a rim with 56 holes drilled in it was not going to hold air. 6 hours later, I managed to get to this point. The 3 screwdrivers you see here are the only ones I have left since I broke my other 2 getting to this point. The entire day was spent hammering, prying, and swearing, but I eventually got the tire on the rim. A good tip is to use a bit of dish soap to lubricate the rubber. It will be much easier to slide over the rim. Because the old tire was baking in the sun since 1970, it needed a little help to brighten up, so I covered the rim with newspaper and tape, and then spray painted the tire with gloss black spray paint. Another reason for spray painting the tire was to get rid of the white lettering on the side. What do you know? The paint actually made the tire look like new. Sure, you could still see the branding a bit, but it was hardly noticeable, and the tire looked like it was new again. If you compare this photo to the original photo of the old tire, you can really see what a transformation this wheel has made. A little hard work can cure any problem. Well, here it is, the fully assembled OverKill chopper, forged from the scrap pile using only basic tools and a lot of hard work. Was it worth it? You bet. Just look at it. The only thing I had to pay for was the front tire and a few cans of paint. It goes to show you what can be accomplished by using your imagination and muscle. The bike rode perfectly on the first trip, accelerating much better than I had anticipated due to its weight. I drove around for an hour or so, watching all the jaws drop as bystanders realized there was no engine on this full-size street chopper. At red lights, I didn't even have to put my feet down. The wide tire kept the bike upright. I took OverKill on many long rides without any problems. I had eventually planned to install a front caliper brake, but due to the fact that I rarely broke jogging speed and didn't have any hills in my area, I just didn't bother with brakes. If you want to install brakes, just add a front caliper brake or install some type of makeshift friction brake under your seat that will rub on the rear wheel when you pull on it. Oh yeah, this chopper gets noticed. I ride up to a coffee shop packed with motorcycles and fancy cars on a Friday night, and OverKill always steals the show. Even the little trimmings look like they were custom made. The headlight is just a reading lamp, and the fancy plugs at the ends of the front forks are cabinet door handles. The entire bike is made of junk or common recycled bike parts. After many miles of rough terrain, the chopper has had no problems whatsoever. I have bounced it over curbs, potholes, and even been down some off-road trails. OverKill is built like a tank, which is what a chopper is all about, and I expect that it will survive whatever I do to it. Well, I hope this DIY video has inspired you to carve up some old bike parts into your own cool custom design. I have 40 more bike building DIY videos coming to this channel soon, so stay tuned. If you would like a printable version of this plan with a bit more detail, browse over to chopzone.com, where you can find a print-ready copy to download. You may also want to check out our Builders Forum, where you can discuss your projects with other bike freaks and find more creative ideas for inspiration. Okay, I'm out of here. This chopper ain't gonna ride itself.